Okay. Better. Why? Okay. Hey.
Hello.
Hello.
Good morning.
Hey. We're filing in. So I had a complete hardware failure, and I'm on my laptop. So pardon any weird things with sound and video while I sort out my laptop for this operation. Yeah. Okay, who do we got here? 2 minutes. So can people actually hear me here?
Yep.
Okay, good. Okay. Yeah, I'm still sorting things, but it's not gonna be too much longer here. So this is, you know, Coffee Compiler Club. Mostly we're going to talk, you know, tech stuff about compilers and language runtimes. I don't have a set agenda otherwise. Here's somebody else. Who did I miss? I missed somebody. Mark Siegelman, that's what I missed. Yeah, okay. So yeah, so I'm here to talk about language runtimes and compilers. There's no set agenda. Conversation comes and goes, and we're done. It's all fine. Actually, it's very similar to like what an unconference is about. You know, just wherever the conversation goes is what you do. I reserve the right to moderate, but that's not been a problem. Mute your mic when you're not talking, so we don't have 20 people with dogs and cars in the background and whatever else going on. As I said, I'm on my laptop today because my main desktop had a hard fail 2 days, whatever, last night, the night before, and then I came in the morning to go do a HydroConf talk, and my main desktop was dead, and I had a desperation last minute put it together on the laptop for a remote streaming thing. It was not a fun moment, but you know, the conversation went well. The talk went well. Oh, there you go. So Cameron, you're voted as being the main talker because you're not muted, and so I have a big view of you moving your camera into the corner. All good.
Yeah, I got kicked out of my office.
Bummer. Doesn't look like
my son's home, and he may have been exposed, so he took my barn.
Oh no! Oh yeah. Goodness! Yes, I'm in the other zone. I went to go visit my parents a couple weeks ago, and my son volunteered out of the house, and he'll be back maybe today, maybe tomorrow after my 2 weeks are up. So he got kicked out. But he's 20, going to college. It's all good.
I'm not going to tell you where I am.
I'm sorry. Yes. Boston. Yeah. Yeah, it's going to be San Jose State. He's at Dianza, and in theory, going to go to San Jose State in the fall. Except I don't have any idea what's going on now. Whatever it is. So if somebody has something to bring up, they can. Otherwise, I'm going to start the ball rolling.
Yes,
We had a fun conversation with the HydroConf folks. These are Russian conference doing concurrent parallel computing stuff. And I had a fun talk about debugging parallel programs, debugging concurrent programs. So debugging data races, talking about formal theorem proving and state machines and model checkers to verify state systems, and the kinds of data races that people write in practice, and the obvious code smells that turn into a data race that are sort of obvious after the fact, but never before the fact. If any of these sound, ring a bell with anybody or have interest, I'll go in deeper here. Like I said, I'm looking to get a conversation going here. So people know what I mean by data race and why you might care. I see some heads nod. I see some not some heads nod. Oh gosh, I forgot to mention, I am recording this. However boring it gets recorded, thrown up live. If you don't like that, bail out. I know there's a lot of old timers are like, yeah, we know. There's some new folks every time. It's like 10 old timers every time, and then there's like 5 new people every time. It's sort of the where we got to here. So
famous data race in Java when you access a hash map from 2 different threads.
Yeah.
Synchronize, and it gets the system into a halt with a 100% CPU.
Yeah, I talked specifically about that one. So I'll go over it again because I don't know if everyone knows what happens here. So HashMap is been around the block, used for caching all the time, and concurrent systems. And there's been this theory that says I got one writer and many readers, and the readers typically hit in the cache, and the cache is caching and doing what it's supposed to do, and the one rare writer comes along and updates the cache periodically. Great. So because there's only one writer, we have this grand theory that says we'll use an unsynchronized hash map, and only the writer is writing. So he'll occasionally change the map, and occasionally the readers will screw up and throw a null pointer exception, which will catch and retry, and by then the writer will be done. So that all works great for a while until periodically the table gets resized, and then the doubling of the array means the size field gets doubled in size, and then the array gets reassigned with a new or larger array that's doubled in size, and the elements get copied. So somebody comes along and they grab the new array and the old size, the hash, and they miss, and they have a false miss. But that's not really the problem, because they'll just go make another copy and reload the cache. No, so the next problem is they load the double size in the old array, and they throw array index out of bounds exception, which they were not catching and retrying. So they couldn't understand where the array index out of bounds came from. But that can be caught and refixed and redone. So the real issue is that 2 readers, if their reprobe is bad enough, will trigger a resize. So independently from everything else, 2 readers who are not synchronized will both try to resize the table at once. Now they're writers. And a common fail at this point is they both scribble the same linked list of buckets in the bucket chain, and they screw it up, and they get a cycle. So when they're done, the rewritten table is mostly correct. Some bucket chains are now corrupt and are cyclic. They go probe, and somebody goes and hits that bucket chain looking for an element, and they run down the linked list, which is cyclic forever, and they never get to the end. So they're burning 100% CPU, but they're a reader doing some sort of transactional thing. Somebody somewhere times out the transaction, decides, oh, this transaction has a fail. I don't care. I don't know why. I'll just run it again. So the server farm pulls another thread out and launches it, which immediately goes to the same bucket, runs the same linked list. Now 2 threads are running down the linked list forever. And then 3, and then 4, and then 5, until your server grinds slowly to a halt with 100% CPU and no one making any progress. So this was, one of the more fabulously difficult to debug operations. And it's just,
I think the data race is by far the most frequent, but at least from my experience.
Oh, really? Okay, most frequent. That's interesting. I had only seen it a few times, but it was always insidious.
I think I saw it about 10 times in my career.
Nice.
Mm-hmm.
Okay. So the other bits of wisdom were the most common race that I've seen is two readers and a write in the middle. So in the HashMap case, if you throw our index out of bounds, it's two writers with a read in the middle. You write the double array size, you write the double length array, but there's a read in the middle of the double size, and you die. The other one's more common. That is, I read it once, I null checked it, I read it again, and I die with a null pointer exception. Because the readers are typically in accessor functions, because you're trying to put meaning to a complicated problem, it's hard to see that the read it and the do it are loading the same underlying field. And so you have accessors hiding the fact that you have two reads, and the test and the use are independent, and then you fail. Except that in the case of a C debug build, you have the two reads pretty commonly, and the fail can happen. In an optimized build, common sub-expression elimination can commonly remove two reads, and you never fail. In Java, you fail if you're running in the interpreter, and you take a bad context switch, which can happen as the system hits heavy load when you're running the code a lot, but you have not yet JITted, and you're doing a lot of context switches. But if you get past that and the JIT has kicked in, then the CSEs happen, and the bug never happens again. So the end result is you have a server that is flaky at startup as load hits it, and if it crashes and burns, you curse and swear and reboot the server. And the second go around, it works because you didn't hit the race, but then it's JITted and it never fails again. And you hate the fact that the server dies at startup, and you don't care because you just restart it again a few times and it goes and it's caught, and you're like, it's done, I'm leaving it now, and you walk away. And this kind of a bug can sit around forever because it's kind of insidious in a different way, and that it actually does not fail once the optimizers kick in. And the moral of that story is, in any of these concurrent algorithms, you have to think that you're doing a concurrent algorithm up front. It's not sort of a bolt-on after the fact, because it messes with how you look at the accessor functions to put meaning. The common example I gave is straight out of a hotspot. It's, does this method have JITted code? Oh, okay, grab the JITted code and execute it. So there's a does it have, and there's a get and go. And the does it have and the get and go use the same underlying field. And the problem is that because it's racy, I can't do it that way. I have to get and test in one set. Having verified initial conditions, I can never read memory again. I must use what I read already to verify initial conditions and go. And that's a different API model. It means typically that you have to have a poison mode on a value, where null is the common poison, but it doesn't have to be null, you need one. You read the thing, you test for poison. If it's poison, you do the fail mode, and if it's not poison, you got it, you go. But you can't read it twice. You can never read the same field twice. And sometimes you have to read 4 or 5 fields and verify a bunch of things. But if you have read any of those fields and tested them to confirm correctness, you cannot read those fields again. You have to go with what you read, or you'll have a data race there. So I guess after that, I ran around and talked about different debugging technologies, visual inspection being the obvious one, formal methods being the obvious fail. It doesn't work because it doesn't work. And then there's a bunch of in-between things. Printing, it gives you the Heisenberg problem where you change the timing events. And the fix for that is that you can make printing ever cheaper. So with a few short hacks, I can get printing down to 2 to 3 clock cycles, like a handful of nanoseconds. And that's generally cheap enough it doesn't blow your race, even in really tight code. And how I do that is I don't print strings, I print tokens, enums, basically, but a token, and a nanotime, which is a read of the TSC register. And you put them in a thread local ring buffer. Why thread local? So there's no cross synchronization, cache miss events. Why a ring buffer? Because there's no blocking for IO. You try to write out an infinitely sized, huge, whatever. You're basically making a log file, but the log's in a ring buffer. It's limited in size, and it contains only timestamps and event tokens. When you've crashed, you have a debugging call that grabs all the threads ring buffers, sorts them by nanotime, and pretty prints your event tokens. And suddenly you get a timeline at very, very low cost. And you can now aggressively add event markers as you home in on the bug, and without destroying the data race. So that's a good one. The other thing that I talk about that's not common, that I don't see commonly done, is you attack random fails with statistics. So if I have a bug which fails once, once an hour, once a day, once a week in QA testing, hang on, I'm gonna grab another person here. Then you tackle it with statistics. So I don't know, I can't get it to fail on my desktop. It never fails. So it's a Heisenberg. It never fails on my desktop. It always fails in production. It never fails in QA testing. What do I do? Okay, so it fails in QA testing occasionally, very, very rarely. We saw it once. So you make a fail box, a box that is going to try to guarantee fail this bug, where you run it under as heavy load as you can, back to back, as hard as you can, continuously, and you let it run forever, days on end, however long it takes. And you're not interested in capturing the bug and debugging it. You're interested in counting the failure rate. Because if you have a statistical bug and you make a change and you think you fixed it, but it only happens once a week in QA, did you fix it or did you not? Well, you can't actually tell, because if you run it on your desktop, it never failed on your desktop before. It's not going to fail now. So you don't know if you fixed it. How do you know you got to fix it? You start with a guaranteed fail box. Oh, let me grab one more guy. So the goal of the guaranteed fail box is to, first of all, get you a failure rate and get you a notion that you can guarantee see the fail. Now that it's failing reliably, you start to add whatever debugging technologies you want, usually prints and logs until it hides the bug, which you see in your fail rate dropping off. And then you go to switch to cheaper printing and assertions and thinking about where to target. And as long as you have a guaranteed fail box, you can binary search in on the fail until you get it tight enough that you can call it to your desktop and see the fail and make it happen there. Once you have a fix, you go back to your guaranteed fail box and run it again for the necessary length of time to validate that your fix actually fixed now. So that was an observation I took from having worked with hardware guys, that there is a statistics problem, there is a randomness problem to the fails. So the statistics is how you solve it. You need to guarantee enough iterations that you are confident that you have fixed the bug, and that might be thousands to millions of iterations for which you crank up a cloud box or a spare server room box and just burn the box continuously running under heavy load.
Yeah. So another one that helps is random NOP loops.
So sleep. Let's talk about sleep.
So no, not sleep.
Oh,
not
NOP loops.
NOP loops. Yeah. So imagine that between every two instructions, you could add automatically a random length NOP loop. Yeah. Right. So it should not impact the correctness of the program. Right.
Right.
So let's say you have a statistic, you see there's a failure that you can reproduce once a week. So what you do is you write something that changes your program. So each time it runs, it's running with a different mix of NOPs. And then when it fails, it takes that mix and shows you what it is. So I've done this a couple different ways, including actually writing a test back out. So the test actually writes a new test for you, showing how to reproduce the bug. So, because race issues are you can burn a lot of years on them.
I totally did in the land of, well, in a couple different lands, yeah. Hotspot was a big one, but I did plenty in other places too. Yeah, so let me bang on sleep because of the fails it has. So there's an easy, not the same as what Cameron just said, where you put sleeps in different places to try to stall delays. And the goal is to delay timing, change timing, and then signature divide. And the problem with using sleeps is that if you put it on a QA box under heavy load, the sleeps may not be long enough to trigger the same bug, or you wouldn't get the interleavings that you were hoping for, because the thread in question that was supposed to run during the sleep zone never got a clock cycle to run. The sleep timed out and started up again. The other thing with the sleep guy is if you put it on your desktop and you begin to single step things, the sleeping thread will time out while you're in your debugger. And again, he'll take off and run and you won't see the issue. So not the NOP thing, but on the same vein is I've used I still use a tick-tock clock-based approach where I'll force a thread interleaving in a JUnit test, but force a thread interleaving. So it's not the NOP thing where you're randomly sorting NOPs. This is, I'm just going to say this thread and this thread and this thread and this thread. In theory, they're independent and free running. In practice, under the harness, they go in exactly this order. They go in exactly this order based on, even if in the debugger, and I can force an ordering. So basically, I force a thread schedule. And so I'll obviously only do it for JUnit tests where I'm forcing one of a billion schedules. But I can force testing that the bounded blocking buffer is full or empty, versus the readers doing or whatever producer consumer things. You can force the different edge cases. Whereas the NOP thing, I swear I have used, but it was not a common thing. I should put that in the slides, actually. I think that's a good one. That's a little different because you can't hide so easily from the stall. You still have the issue under heavy load, you might not have enough stall in the right place, but it doesn't just completely disappear the way sleep does. It's definitely a better thing. I know I've used it. So the other thing I did is shit like, network, inject failure injections. We're doing races and clusters. Oh gosh, damn it, I didn't hit the go button on this dude. One more person, there it goes. Doing data races in a cluster. So inject network failures, inject delays, which is just versions of sleep. What was the other major game there? Just having enough nodes in a cluster to force cluster collects was necessary in testing. If people would test clusters with one node and two nodes, and I'll recommend as a lower bound 5. Having done 3s and 4s, you get 4s, you get divided by 2 things too easily, and 3s, you get man on the left and man on the right and man in the middle. But there's not enough. But the man in the middle might also be the top of a tree or the side of a tree or something, but he's not. You don't get somebody who's in the middle of a tree if you're building a tree structure out of your cluster for communication purposes. The common, you told 2 friends, who told 2 friends, log scale broadcast. So what else? It's a good hour-long talk. Oh, load factor things, but that's sort of the same game. There's another one where you know it's supposed to be concurrent, and you do it in a unit test for 1, and you do an X, so you see the Y works. So then you run it in a loop going 10 and see the 10 Ys work, and often a lot of bugs show up because it's the first go around when you're doing things. But it's totally useful then to do the million. Once you can do 10, just crank the knob up to, crank the knob, the amplifier to 11, do a million in a row, even if it takes a day, because that will do a different kind of stress. It will hit all your edge cases over and over and over again, with the theory that you now can find a lot of much more rare bugs. And if you can run it for a day on end without it falling over, maybe you got the issues out for a production service. It's probably a whole lot safer now.
I'm actually kind of interested how you would implement the thread interleaving you were talking about.
Oh yeah, so you put a global clock counter down. Well, let's see here. I have slides, but they're probably actually in the next setup here on the old lappy. You have a clock word. You have a get. Here we go. You have a block until you get a clock timer. Block until, I'm gonna have slides here in a second. They'll help a little bit. Static analysis, distical, distributed. No. Writing date duration. Here we go. white box testing. That's my white box test. Yeah, this is a good example. Let me see if I can share it now. No. Right here. Yes, share. Yes. Oh, and there's a chat window. God damn it, I'm so far behind here. There we go. Kernel. Oh, okay. Something else going on there. I'll look at that in a second. Yeah, here we go. Share. Okay. So you make a global variable. You have some calls. So in this one here, I have a bounded buffer queue, and I'm trying to force the buffer's full issue. So somebody puts in the buffer, and then they're waiting for thread one waits at get tick until all other threads block, including thread 2. Then thread 1 gets his tick and decides he can go, and he wants to put a second element in, but he should block because the buffer's full. Thread 2 wakes up and tries to do a get, and he's going to get the first element, and then he wants to get the second element, but so what's the ordering I'm missing here? The first guy, thread 1, won't claim victory until he's done. I need to have another piece. I ran out of slide room. He needs to say he got it all and the buffer's empty now. The point here is that the one guy advances. Everyone blocks until you caught up to the get tick. The get tick says I now go until the next get tick, and the wait for is waiting for tick 1. I gotta wait for tick 1 to happen. So then he blocks until the other tick happens, and that can force an interleaving anyway. But basically, you have two calls. One of them is get the current value of the tick, block until everyone's done moving. No one's moving. Okay, now get the current tick and bump it by 1, and get out. And then carry on. And the other guy says, I wait until I see tick 1, and then I get out and get on. And I can ping pong people with these kinds of operations left and right. I can also do get tick and cross multiple different threads to force really one by one. Here I'm lining up for a data race between the put and the get of the second put with the first get on what's supposed to be an empty, a one element queue that's now full. So whatever you want to do with
missing something. What does get tick mean, and what does it mean to wait for a tick?
So the get tick means wait until everyone's blocked. I'm blocking. So get tick says I'm going to block, and I know there are other threads in the world. They also need to block. So I'm doing a barrier synchronization call under the hood. So I have to have the set of threads I'm blocking on because I'm running all my tests concurrently, and this test plays parallel with unrelated tests. I have a global variable. Let's say global. A global variable is global to this set of threads. So the set of threads involved in the synchronization. So somewhere under the hood, there's a clock thing that I have made that has a list of known threads that need to block or not. Then a thread, when he's going to block, says I'm blocking now, and takes does a wait. When the last man goes in, everyone's blocked. Then if he's a get tick guy, the guy who has we all get our wait. We wake up, we do the check. Are we the one thread who's expecting this tick? If we are, we bump the tick counter, we notify everybody, and we release the wait cycle and we run on. And then other folks decide if they're supposed to wake up or not. So I don't have an implementation on the slide. I have a use case on the slide, but not an implementation. So the implementation is there's some sort of bulk synchronized guy or bulk barrier sync going on. There are JDK calls to do exactly that. I don't have here. I'm inventing one on top of my head, but the goal is simply bulk blocking. Everyone wakes up and checks a condition. The condition is I'm expecting this tick and I'll bump it, or I'm expecting this tick. And if you get your right expectation, you run forward. And if you bump it, then somebody else can now go. And so you can force threads to take step by step back and forth, and you can force them to align and then race forward. So you can have them race forward, you can have them single step, but they can tightly race forward. The goal here is a tight race forward. They perfectly align They both simultaneously, it's not simul, they wake up from the notify, they check their condition, they agree it's okay, they unlock, the next thread wakes up, checks the notify, agrees it's this condition, unlocks. It's very close in time. It's not a perfect time, it's very close. If you were to run those narrow races in a loop, you'll get any data race that's within, you know, a couple hundred clock cycles thereafter. That's all the time it takes for two threads to wake up and race. So you can narrow races very tightly here. And you can also just force an interleaving. I do thread 1, I do thread 2, I do thread 1, I do thread 2.
Is it like a phaser in Java? The implementation?
It's probably it's probably the right thing. It's being used for debugging. Like I said, there is something in the JDK. I grabbed a thing that I did this years ago. I grabbed a thing that phaser wasn't around. I grabbed whatever was there and I did it. Let me kill share here. Kill that. Yeah, so I know there's something in the JDK now. Phaser sounds like the right thing. I don't know what it is. I don't have an implementation in hand. It's a tool I used when I needed to do reliable thread schedule debugging. Phaser, here goes. Somebody says phaser in the JDK. This sounds like the right thing. Yes. Yeah, you have to register. Oh, you can vary registration. Okay, yeah, fine. Yeah, this is the right kind of thing. Yeah, just use it in writing JUnit tests where you want a single step shift forward. So another good bad failure in JUnit testing is the standard thread.join will throw away an exception if the joining thread died because it threw an exception that rolled out the top. So if I have a JUnit test fail that says assert equals blah 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 condition, and I'm running multiple threads, I fork. One guy runs down, he says, JUnit assert fail, I die like a pig now. And he throws an exception that you're not catching and doing something else. It goes back to, with a thread join, back to your main thread who promptly ignores the exception because it doesn't get passed and declares victory, the test passed. And so the test lies to you. If you have a remote thread you're kicking that has a fail, it needs to set a volatile variable saying I died now that you can pick up and test. In the main thread running the JUnit test, or you won't get it. The obvious thing to put there in the volatile is the actual exception you got. If anyone dies, write your exception in this variable before you disappear. Let's see, cause randomized scheduler. I have heard of this concept. There's from Matt. Yeah, I mean, the whole thing of throwing down sleeps and running under heavy load is to force random thread scheduling. Like the guaranteed fail box is all about forcing all possible schedules via bulk iteration, and under the assumption you have enough randomness in the system already, the butterfly effect takes over and you'll never repeat the same schedule twice, and eventually you'll touch all schedules and get the failing ones. If you're too good at your reliable test fail box about reiterating things perfectly exactly, then it'll always run the same schedule and you won't fail and it won't work. So Ham, what did you do that you were seeing concurrency failures? You were talking about the HashMap fail. What were you doing?
For 8 years, I was an independent consultant helping organizations to solve performance problems, mostly in Java. And you see it again and again.
Unsynchronized HashMap, really?
On unsynchronized HashMap, yes.
Yeah.
It happens quite a lot. And usually people don't really know how to deal with it. So
you just tell them to use concurrent HashMap and walk away?
Yeah.
Okay, fine.
Like when you know what you're looking, it's like 5 minutes to solve it, right?
Yeah, fair enough. First time, it took me a long time to figure out what the hell's going on. But I could see after that, it'd be pretty easy, pretty obvious.
I can even guess that it is the case before I look on the stack trace, because it has a very common behavior. At some point, a single thread goes to 100%. Probably a few hours later, another one will go to 100%, and it never ends. And it's has a very high correlation with such a case.
Interesting.
I am not familiar with other cases that go to 100% CPU on the JVM.
I can tell you one, but it's a very different use case that I've also run into. This is people using some sort of hash table with weak references to do, that have to GC control the size of the cache. And then the failure is the server is very busy, the cache is full and caching well, and so the server is handling all requests in real time, it's all fine. Then the load bobbles up a little bit, there's a GC cycle, the GC cycle cleans some stuff out of the cache because it's weak refs. So now the server, which was very busy and using that cache, misses. The miss requires doing a lot of work that requires a lot of GC effort to rebuild the element in the cache. Well, during that, you're already under memory pressure. The GC runs again and cleans some more elements out of the cache. Then the server does more work, and then the GC runs again and cleans more elements out. And you get this vicious cycle where the server is furiously running as if the cache were empty, because it is. The GC is furiously running because he's out of memory, and so he's flushing the cache behind the server constantly. And the server never makes any progress because it's always cache misses all the time. And you're running 100% GC cycles back to back to back, which is flushing your cache constantly too. And that carries on until you kill the load to the server. And then if you apply the load to the server again, he starts caching, but because the load was low, he didn't have to do a GC and the cache can catch up. And then you can ramp the load up to the server and the server can be fine again. But you have to kill the load to the server for him to ever catch up. So that just goes to the moral of that story is using GC to manage a user mode cache is kind of a bad idea because the GC has no fucking clue about your cache or what's a good caching strategy and when he should evict and when he should not. So he sees a weak ref and he has no idea what to do with it other than to say, it'd be nice if I had this memory back. And so he whacks you. But he doesn't know LRU from whatever kind of caching strategy you have versus whatever. So he whacks the cache willy-nilly. You'd rather have a callback that says I got low memory and you run a user mode intelligent cache flushing mechanism, right? Like I might have in-process web page requests that are going on that I've cached early events that I'm going to look up in the cache again while I'm waiting for the database to come back. And the GC will just, wipe them out, even though you know for a fact they're going to be used very shortly in the future. So you don't want the GC dictating your caching strategy.
If you go back in time, will you cancel the feature of weak references and soft references and all of this?
But if I go back in what?
In time.
Back in
Oh, yeah. There were, yes. There were, like, it was a good try at a specific idea that didn't work out well in practice. Same as finalizers. Like, there's a cool idea there on finalizers, but the actual returning of OS level resources is best done with essentially malloc and free with helpers. So, C++ destructors, lexical scoping, right? Or reference counting, but not the GC. That's a different fail. But yeah, I would bang on weak refs. I'd say no. So I sat next to the guy when he was trying to do, C4, do GPGC concurrent parallel background collector at Azul with read barrier base. And the change in how GPT works, the major change is that full GC cycles are relatively cheap, at least to the mutators, and we run them all the time. So if you run a full GC cycle all the time, every time you write a weak ref, it can be on the clock cycle later, the GC wipes it out. Now, that behavior ran so badly with so many other people that we had to do something about it. So if the GC comes across a weak ref and he's low on memory, so he cares, he won't throw it. he puts counter bits in it and counts GC cycles since that last weak ref was visited and is alive and only weakly alive. And after enough time has passed, then he tosses them. So he does an LRU behavior really based on lifetime. It's not really LRU, it's because he doesn't know the usage of the thing. He just has a drag time. He lets weak refs drag on a while. Otherwise, the spec says they can be cleaned out on the clock cycle.
Isn't that soft that you're talking about?
I'll have to go look up. Weak, soft, and fan are all slightly different, and I have to go stare at which one is which. But
Yeah, soft is the one that the GC makes a decision about whether or not to take. Weak simply means that no one else has a reference to it, so your reference no longer keeps it alive.
But it doesn't go away unless the GC decides. So soft is the one that you're saying, soft is the one, and I totally believe you. Soft is the one, I'm just repeating to make sure we're on the same page. Soft is the one where GC can set it to null, and you have to test. Weak refs are the one where no one's got a strong ref to it, so no one can notice that you've set it to null.
Right.
But you can invent a ref to it because it comes out of caching. Right?
So the idea is when GC runs, if no one else has a reference to that object, at that point, you will be able to detect that. So basically, you find out that no one else has a reference to it, and then it does a. It's salvageable at that point because you have an event where you can reestablish a strong link to it. And there's 10 billion lines of code, patch upon patch in the JDK to deal with this.
Well, yeah. Right. There's a thing to bring it alive. There's a thing. See, I want to say it's weak though. There's a thing in the weak that says I have a weak pointer to it, but I can make a strong pointer from a weak pointer at any point in time. A mutator can make a strong from a weak at any point in time. And the common thing you do is you have a hash table, and you look up and you find the weak ref in the hash table that immediately makes a strong ref on that clock cycle.
Exactly, right. So, but that strong ref is basically on your stack. So basically, as long as you're working with the ref, you have it. And then
That's not what I'm saying. I'm saying that's not that. The bigger picture here is the GC, the Azul GC would discover, in fact, it was weak. You do a hash table put with a weak ref only, then you run immediately afterwards and do a hash table get of the same key, expecting to get the same value back. When you did the hash table put with a weak ref and you didn't have a pointer to the object, but you had the key, but not the object itself, on that clock cycle, Azul ran a full GC cycle behind your back and wiped it out. So the next line of code, you say hashmap.get, and we correctly have wiped it out. And you get back a miss in the hash table. But you were not expecting a miss because you put it in just the line before.
Because there's no other reference to that object in the system, you're saying?
And so you crash and burn. Your application crashes and burns because it was unprepared to have the object wiped out because you didn't hold on to a strong ref at a point. So the difference here is that in an Azul collector, full GC cycles happen about every 20 to 30 seconds. They're really rapid. So it's a different model altogether on how the GC works. Fine. And obviously, you don't walk the entire heap every 20 to 30 seconds, but the effect is you get a full GC cycle effect every 20 to 30 seconds. And in fact, you do walk huge amounts of the heap, but all in the background. So fine. But the implication then is your applications died, and people were just not prepared for it. And so we had to make random crappy Java code run. And so we put drag time on weak refs. So that complicated the algorithm a lot. You had to have counter bits on object headers for weak ref counting, or you had to have somewhere to put counter bits on weak objects, right? There weren't enough bits in the header, so you had to do something. I remember the guy sorting, sweating bullets trying to figure out what the hell to do here. And this is one of these cases where 90% of the applications don't ever care, and 10% or 1% care a whole lot. And you have giant caches of weak refs and have millions and millions of weak ref objects. So, small tables of weak refs and lists of them were great for 99%, and 1% case died like a pig because it didn't have an efficient implementation of storing bazillions of age bits on weak refs.
Yeah,
when I was working on J9, similar with the soft refs, because hotspot clears soft refs on the amount of megabytes of soft refs that are allocated. And it's some weird, I never even looked into exactly what it is. But in J9, we just counted GC cycles. So, and we had a default age, and that age kind of varied based on your heap occupancy. Like there was a max age, but if you're really full, that age was lower. But right away, we had to turn it off for the generational collects because if you had a really large overall heap, but large residence set, like you have a big in-memory database, but you got your nursery, so things are living 2-3 cycles there in the nursery before they're getting moved to tenure space, or they're all dying before they move. But the heap is so full that it was actually looking, our age was all the way down to like 2, so they were being cleared on these caches while they were still used. It was the exact same thing. We weren't doing exactly what Hotspot was doing at the time, so like we broke a few places, but we broke them terribly because they were just expecting that behavior from the reference objects. And similar to weak, we had something there as well where I spent, I don't know, weeks and months trying to like make this work the way we made it work, but close enough to how hotspot behavior worked in these applications so they could work again.
Yep, I totally believe it. Yeah. If you asked me to go back in time and kill weak refs, yes, I would.
Well, the benefit of the weak ref isn't so much I haven't seen it used in caching in the way that you have, but the big benefit of it is the event, not the reference itself, and that gets taken advantage of. There's I'm sure you'll know it off the top of your head. There's a weak HashMap or something like that. Yeah. And basically what it is let's say you have an object, and as long as that object exists, as long as someone has a reference to that, they're going to come back to you and ask a question, and that question is super expensive to answer, right? So you cache the answer based on the thing that they're holding, and then when the thing that they're holding goes away, you want your cache entry to go away. Right. And that's where weak really comes in handy.
That puts the weak on the key instead of on the value.
Exactly. And then it uses the event on the key to clean the entry out of the table.
Right.
Does that ring a bell for anyone?
It does. There's like this freaking thing called reference queues, where people that pass certain certain events get thrown on a queue that Java thread. Yeah, Hames like thumbs up. Great, thanks. Java user mode Java code runs those queues and does something intelligent like cleans your hash table out. I remember dealing with that kind of stuff at different points. Like I said, this is one of these things where if I were to redo it, I don't know what I would do, but I would not do that. There has to be a better way. Yeah, Charlie's laughing at me now. Yeah. Now come up with a better answer, but do it 20 years ago. Like if I went back in time, I would go bang on weak and soft refs and say, no, bad idea. But I wouldn't have the evidence in hand. I would only have the theoretical discussion, right? Yeah. So I couldn't have actually changed people's minds without some hard evidence in place. And that's sort of the suck thing.
I don't think it was a bad design mistake. I think the challenge is that it was a build block and it just wasn't much built on it, so developers ended up having to use them directly, and that caused all sorts of problems. Just slightly too low level for your typical developer.
Right. There were a lot of interesting mistakes, I would say mistakes made at the 20 years ago because we just didn't know. So because they're not a mistake. In hindsight, it would do it different. In foresight, you couldn't. So what the hell? It's not a mistake, but yeah, I'm all happy to have something different.
Because I think phantom references I have no use for, and I don't mean that in an insulting manner. So
right.
That was an objective statement, not a subjective statement. So I actually have to go back and read the doc every time I have a question about phantom references, but the weak references are useful and soft references are theoretically useful. They're just not useful because Hotspot doesn't let them be used. But in theory, both weak and soft references are brilliantly good. Phantom.
I'll claim that I'm not there. There has to be a better answer for what to do with it. You're asking, the deal is, for me at least, the deal is you're asking the garbage collector to manage something, which I guess we got past.
No,
So reference clues, you get past that.
I'd explain it differently, which is you're giving the garbage collector an avenue of last resort instead of crash, instead of throwing out a memory. And in that sense, I think it's actually quite like a soft reference would be quite useful. So, because the contract as a developer, when I think of reference makes perfect sense. It's like, hey, if you're GCing and your choice is, shut down my application or take an item out of my cache, yeah, take an item out of my cache.
Right.
So there's
as just explained, what then happens that you still fail. You just drag it out and make it very difficult to diagnose what the fail is.
Right. So taking it out of the cache and not providing event feedback is probably a bad thing.
So, all right. So if we go to the zone where I tell you that it's not being touched by, it's weakly alive only, and now you act on it, then the application is being fed information and makes its own choices about what to kill and what don't. And there I totally agree.
And the challenge
that's
too
a
is
different zone. That's a zone where GC is informing and not acting.
Because what happens is you usually don't get into that situation until it's already too late. Because what'll happen is you'll see a GC, they're every 5 hours, and then they're every hour, then they're every 5 minutes, then they're every 30 milliseconds. And at that point, it's like, oh, I need to do something. And by that point, you have so little working set left, so little working space left that, like, if you hand it over to the developer and say, hey, you fix this, the developer can't put together an exception without crashing at this point, because there's just no space left.
Right.
So the key is to not let it progress into that red zone if you're going to hand it back to the developer to fix, I guess.
So one of the things you said there was you have this, GC cycle in 5 hours and then 1 hour and whatever. It's instead, I would like people to think that instead it's about the fullness of the live set or the size of the live set and your sort of leak rate. Because in the Zool box, you're going to get that GC cycle every 30 seconds, every time. And what instead happens is we burn more and more cores. Instead of stalling 5 hours, burning no cores, and then burning a whole shit ton, and then stalling for an hour, burning no cores, then burn a whole shit ton. It's the case that you get more cores burned in order to keep up until you run out of cores to keep up with the collection, right? So your mutator starts taking stalls because the cores are all burning trying to do GC. So it's a different trade-off, but in both cases, the common failure is the working memory and the live set is too large a fraction of the total heap size for some sort of efficient GC management. And that typically is the case of, I guess you can underspec something, but the usual answer is you're leaking. You can underspec your heap, right? You can try to crush the heap down and force yourself into a corner. That happens. But I think it's a more commonly that you're just leaking, and you decide how long you're going to run with your leaking rate until you die, and then reboot anyhow and take the giant GC cycle that happens on a reboot, and or fix your leak.
I wonder if you could do something like when you claim the resource pointed to by regraph, you claim it for a set amount of time, and if the GC tries to clean it up during that time, it says I can't clean it up, so it's gonna crash.
So you have some weak refs and you're low on memory, and the GC looks and decides they're actually weak. Now what do you do? So Cameron's point is, if you wait too long, you're too low on memory, and the application developer can't actually do anything. You got no working state. So somewhere before you hit to the bad spot, somebody has to make a command decision on this weak ref to throw it or not. The only thing that GC should, in my opinion, should do is tell you it's weak now. Now what do you do with it?
Yeah.
So periodically you wake up and go look at all the weak refs and age them yourself and decide I haven't seen this weak ref used in a long time because I have my own LRU notion that the GC is not aware of, and so now I blow it out. So Cameron's point of, the answer was really expensive. It was a database call that took 2 minutes to compute, whatever the answer is. The answer's held strongly alive. The key is weak. When the key goes away, I'm going to ditch the answer. Okay, the key's weak now. Do I ditch it at this clock cycle? Well, that's too hard to compute. I can't tell you it's weakly alive at this clock cycle, but I might be able to tell you it's weakly alive in 30 seconds or 5 hours or whatever. Wait, is B back? B's not back.
Isn't that Nicola's daughter?
Yeah. Is it Nicholas? Oh.
Nicola. Yeah,
Sorry.
he was playing with his unicorn.
I missed that. Oh man, I'll have to look at the video now. Oh, you know, this is a land of the, you know, stay at home everybody's. And
Nicola, you're on mute.
Oh, yeah.
Opened the wrong thing. Yeah, I was saying my daughter came by the stairs and what are you doing with my unicorn?
There was a BBC broadcaster, whatever, anchor talking about whatever news event. And the background, he's clearly in her home office. In the background, a little girl comes in and is trying to put the unicorn on the wall behind, right in the camera's view, or down low, or she's moving it back and forth, trying to adjust. And finally, the announcer says, "Hey, tell your daughter, I think the unicorn belongs here." It was like live TV, you know, BBC live TV. It's like, okay, live news. This is all very, very cute. I think we all need a little healthy realism in our lives.
Now that Nicola is here, I kind of wanted to ask about some of the stack allocation stuff. I guess Charlie just left, unfortunately. But
Yeah.
I was looking at the JEP draft. I don't think I read all of the appendices, but you were talking about how if you have, for instance, an array allocation that's non-escaping, but the input, the size of it is a phi, or it can be one of two values, one of which is constant and the other one of which is unknown statically, how you would need to rewrite that to split basically the allocation along both control paths and have two separate ones.
Mm-hmm.
That I wouldn't say that seems reasonable as an optimization to implement as well, instead of rewriting in Java. But I was also wondering if you have thought about just taking the dynamic size and trying to do a stack allocation as well. So if the size is not statically known.
Mm-hmm. Just to insert our own check in head and say, hey, if this is the case, do this, kind of fake it.
I was thinking more like you don't know the size of the array when compiling, but you can, if you know the size at runtime, you just bump the stack pointer and then you have your allocated space. And maybe if it's too large, you go to the heap instead.
Yeah, exactly. Yeah. So yeah, I think we're talking about the same thing. I just maybe use the different vocabulary. So it's actually putting an actual check by the compiler so it will check at runtime. If the size is this, do stack allocation, else do this.
Yeah, exactly.
Yeah, it could be done. Yeah, that's the two kind of approaches we were considering. The splitting of the control flow or versioning, whatever you want to call it, seems a bit more general. It may be applicable in other cases where you can benefit from knowing the array size, right? Maybe unrolling can kick in on a loop, knowing that on this path it was constant.
So at Azul, I exactly made those calls. I had stack allocation, as I mentioned before, I was getting a fairly large percentage of all objects stack allocatable by doing escape detection, but you came to objects that were stack local, but they could be very large. And instead of going to the general heap, I kept an off-stack thread local heap.
Okay.
To throw those things in. The other thing going on is I actually had to do a thread local generational PC as well. Because I was getting 70% of all objects, so I was churning pretty fast. The same problem as everyone else. You have a lot of older objects high in the stack that were big arrays that never moved and never got mutated. And you had the shallow end of the stack, which is changing constantly. You didn't want to go revisit in your thread level GC cycle a 1,000,000 entry array element that was a whatever. Thread local, and that was sort of
Cliff, it sounds like your microphone just exploded and now you're barely audible.
We can barely hear you.
Testing, 1, 2, 3.
It sounds very muffled. Maybe something is covering the microphone. Maybe it sounds like that.
Nothing has changed from my end.
Okay.
I have nothing. Yeah.
I don't know.
Again? No, it's a webcam on my laptop, and I was talking a few minutes ago about this is a recent thing. I have the last 30 seconds or something.
Seems better now.
It's better. It's the interweb. Somebody took up the donkey and ran it back. Yeah. Okay. I was trying to say. I had a clicker. I did thread level allocation with a very aggressive strategy at a dual. I ended up having to do a generational collection. But I would take large objects. I would ask the size of an object. If I didn't know the size, I put the size into IR to let it constable. If I didn't know the size, there was a task committed then, and the task would pop up go to the thread local helper function, which was allocated in thread local.
Yeah, but I think both of the things we want to try. So it seems like your thread local idea is more along the lines that we got asked to kind of consider from some of the Hotspot compiler guys using an on-heap version of this rather than putting it on the stack. It's
My
interesting.
problem is I was using escape detection as the primary mechanism instead of escape analysis.
Okay.
So I have to test that an object escapes to the heap at obvious escaping points. So if I decided that an array was too big for my local stack and I put it to the heap, it escaped. Now everybody it touches also escapes. So that blew out most of the thread local storage that's happening on this one thread. So I had to have it in a off stack and off heap area. And that's turned into, I had thread local heap. I think, well, be efficient. I'm trying to say, I went back and forth, but I think I ended up as really just allocated private storage area. The efficient escape detection is basically looking at the pointer structure. You know, I stole bits out of the pointer. I allocated them in a non-heap space, and you can tell by extracting higher order bits out of the pointer and deciding they didn't land in heap mount. And so there was a little bit more cleverness in that, but not much. So I had a cheap escape test. But I couldn't put it in the main heap, and I couldn't do a bunch of other things. I had to fail or pass my heap test, whatever that test was, because there's an efficiency issue on it. That's another read barrier game that you can get fairly cheap on an x86 if you boil the bits down.
There was another thing suggested on the mailing list. I was wondering if anybody actually had tried it before. Suggestion was for loops. If an object is allocated in a loop and you can prove it's not escaping the loop, could you potentially just reuse the last heap location of this object rather than doing anything fancier like stack allocation?
No, that would be, I think the C2 I left at Azul would have done that. That's basically hoisting the allocation outside the loop. So if you have a loop body with a new and you have a use, you're done with it.
Yeah.
You hoist the allocation here, and now the lifetime goes to here.
Yeah.
but you just recycle the bits. No, I was doing that kind of shit as well. But yes, you can do that.
Okay.
Yeah, I don't think C2 currently doesn't move any allocations around, as far as I'm aware.
The Azul collector did. I made an allocation straight up normal ass node in a lot of ways, and it was subject to all the usual node like procedures, including looping gradient code motion.
Although for the allocation, you need to have the interpreter state, the deopt state available if you want to move it, because you can move it across side effects. Did you have it available in C2 easily? So that's why you could do it?
Yeah. Yeah. C2 tracks all debug info sort of in a cheap ass fine grained way. This is my son that I picked out. He's probably going to come over today. I haven't talked to him in 2 weeks. Hey. Yeah, and I'm on a live call, so quick or come over. You're okay to come over.
Tell them where to put the unicorn.
Yeah, call me back in 30 minutes or not. Okay, love you, bye. Exactly. Life goes on. So it's been more than 2 weeks, I've been told. I believe it, yeah. It's time. I have mail for one of my sons, and that's the other son that's living here. He was living here when he was going to school, but school went off. So he's living at his mom's in the summering house. I'm just going down and what's off. I don't know what's going on. He'll figure it out. He's an adult. Just live or die. What were we talking about? I'm sorry, I blew it. Oh, Charlie is back.
Hoisting allocates that.
Yeah, hang on. Hey, Charlie.
Yeah, I told him to come back.
Yeah, and I'm waiting for connection. Okay, hey, you can hear me now, right? So somebody had a question exactly for you. We were just talking about stack allocation and allocating things off heap versus on heap versus state detection or moving allocations out of loops, whatever. Somebody had a question.
Yeah, I guess I asked if you're doing an array allocation that's not escaping and the size of the array is unknown and it's either a constant or it's some other dynamic value. In the JEP draft for the stack allocation, you were talking about having to rewrite some of the JDK libraries to basically split the allocation along both control paths, clone the allocation. And I was wondering, it seems like a reasonable optimization to just do that in C2, but I was also wondering, I guess I didn't quite get that across earlier to Nicola, but even for the branch where the size of the array is unknown, if you couldn't just do the stack allocation anyway, where the size would not be known in advance, but basically you just compile it as a bump of the stack pointer, and then you have your allocated space for that. And then maybe for the constant case, you just do the normal thing with the box log node.
Runtime chat.
I got no sound. I saw you unmute.
So I'll go because I think Nicola's volume is low or something. I couldn't hear him. The changes to the class libraries were kind of just a proof point to us that, like, why are we missing all of these obvious cases? So we just went and changed the class library code so that we could get it. I actually think some sort of hoisting operation or something could be done in C2 to like move that or split it somehow. But we also were thinking along the lines for like a further improvement to stack allocation, because it's not just this simple case where it's like your default size of the array is like, let's say 10 elements, and then you can have a dynamic size for something else. There are a few cases where we saw in the code, just running lots of different things through, where your size was somewhere between 0 and 10 elements. It's not known to be that, but we were also thinking at some point we could like try, well, if you know that, or some large percentage, say like some large percentage is always 20 elements and under, we could put in a guard and do the stack allocation at runtime if it was at your 20 elements or under, otherwise fall back to the heap allocation. But that was going to be a lot more work more than for our initial prototype, and we just really wanted to get stuff out. And I wanted to talk to a few more people and do more investigation to see if it would be worthwhile on doing something like that, how frequent that was really the case.
So can I up level a minute here? What is your goal here? I guess I'm hearing a whole lot of, hey, we're doing stack allocation aggressively now, and I have a lot of experience with this, and I wanted to find out if that's the case or not.
Sorry, my side broke up here. What was your question, Cliff?
What's the stack allocation Jeff about? I see the hit in there.
Basically, reducing latencies and garbage collection was the main goal for us. That was where we really started off, because with stack allocation, you're probably not going to get a significant improvement on overall throughput. Like, it's just not going to be that huge. It's a small win around some cache misses and things, but the overall goal for us was to reduce the frequency at which you do a garbage collection.
Okay. So a couple things. One is, I had tried really hard a decade ago with Joel to do a stack allocation with escape detection, and I could get 70% of all objects stack allocated. But it was really hard work, and there's a lot of interesting non-obvious. The other thing is, there are some very interesting and, way more popular than you might believe use cases where stack allocation can remove memory bandwidth costs to an extent that you get integer factor speed, not little bits.
Mm-hmm.
So I do this all the time with big data streaming things. If I'm streaming data and the data I'm streaming is much larger than my caches, and I allocate per whatever, if I do without stack allocation, you can suck really hard. And if you get stack allocation like effects going on, you can get 5x speed up, like big numbers. So take your grain of salt here however you want. I do have a lot of, I have a talk I gave a decade ago, like it was too early, on the pitfalls, the success and pitfalls of escape detection for stack allocation.
Okay, cool. Yeah, I know there's lots of areas where we can probably, if the right objects were stack allocated, you would also get a significant performance win as well on lots of workloads. And I think we've seen a few where you can actually get a multiplier on the wins. That's awesome, and that's an extra benefit. And I think that's more of a selling feature for actually getting it into Hotspot than going after improving tail latencies on some services to reduce their 5 nines or 90% P90 latencies. So I think that is also would be very useful if we could get that in more places. I think there are significant improvements still to be made to our prototype, but until we have something out that people are looking at, no one's going to if we did the whole final solution of what would catch a lot of these applications at 2, 4, 5x throughput, when we showed up with that, it's going to have changed so much places in Hotspot that it's basically an unreviewable change at that point. We'd never have a prayer of getting that into C2, I don't think, at that point.
You're talking OpenJDK, or?
Yeah, into OpenJDK.
Yeah, I tried to push stuff back to the open, back in the day, and it didn't take.
Hey, Cliff, I gotta ask you, do you have anything published on the work that you just described on escape detection and the work at all?
Not literature published. I have talks I've given in public forums. I have the slides. I'm willing to do them again. This is not now, but we could have a unrelated, just a Zoom talk where I rattle off slides for a while, because of the flow rate information is a lot higher, and then turn into Q&A afterwards.
Yeah, I would really. That would be so amazing.
Well, why don't we schedule that for next week? I'll throw it out on the Twitterverse, and just plan having a you know, half an hour of me rattling slides, and then we'll just pivot to Q&A.
Yeah, that would be amazing. That would be
Awesome. Because I think for me, one of the big areas where we need to put more effort into improving is stack allocating objects that are happening within a loop that feed back into itself. So like just a random counter in the loop, you're adding one to the same local variable in a boxed object. That one's kind of easy because it only has one field and it's only loading back, like there's one part. But like that type of stuff, if you like, especially if you have any like stuff in that, like, because that's one of the places where I think we need to put a lot of investigation in, because right now, basically, if something feeds back to the beginning of the loop again, we basically just don't stack allocate any of those pretty much, which we're missing the largest part of the win, I think, right there.
I burned a lot of time on that one. I ended up looking at like basically putting a new stack frame for the loop body.
Okay.
Right, and then you had to like partially peel the loop body to get the alignment of the lifetime to the correct lifetime to bake a stack for the body. There's a bunch of shit in there. It was like really pain in the neck. It kept getting me further down some edge cases. I did that piece, and I didn't put it in the slides because I didn't get all the bugs out where it was running 100%. It ran my poster child really well. Like the poster child case is all victory, and then you'd have some badass fallout cases where it was doing the wrong thing all the time. And so, I went back and forth between that. I hacked C2 to hoist allocations and do a bunch of other stuff, combine allocations, allocation nodes in C2. And the standard Azul collector kept getting better and better. So eventually I said, I'm not winning against the standard Azul collector, not really. And that was 15, 20 years ago. x86, the trade-offs are different, and I probably could win pretty well against the standard Azul style collector on an x86. So I said stack-based allocation, SBA. SBA would win well now on x86 because the trade-offs are different. The old Azul box had PC cycles out the wazoo and memory bandwidth out the wazoo, and so you didn't care about the memory bandwidth piece at all, and you didn't care about background cores at all. So you go beat that in your stack allocator. Well, it was a tough one. That's not true on an x86. Yeah, that's time to revisit. So I'd be happy to tell you what I did, but I totally fought hard around loops because it was the obvious big win or not big win was to get the lifetime right around the back edge of the loop.
And I think if you're talking about stack allocation for loop case, if you frame it as first allocation hoisting, so you can prove the legality of hoisting the allocation out of the loop, then it looks like you just do stack allocation for this thing which you hoisted. So if you split the problem this way, looks like you don't need to think about stack allocation and loop interactions.
Right. If you move the thing out of the loop, you don't care to have a separate loop allocator for it because it's now all the hard work's gone and you just throw it in the normal stack. Once it's out of the loop, you just stick to the beginning or whatever. You put it on the standard stack.
Yeah, and it is useful anyways. Let's say even if it escapes at some later point,
You want to hoist it out of the loop, that's the big win. And everything else should follow the normal route. Yeah. So the other thing that you missed, Charlie, was people would make large objects that were thread local that because I'm doing escape detection in my solution, I couldn't put them on the general heap because everything they pointed to would now escape. So I had to have a region which was off stack, but was thread local. So I had a thread local heap. And then I had to do generational on the thread local heap as well. So it wasn't individually, it's all easy concepts. It was just, it kept being more and more. When I got generational on a thread local heap with, things hoisted loops, I was getting my 70% of all objects stack allocated with good performance. There was obviously room for improvement. know, it was what it was.
Yeah, that was one of the suggestions that are asking us to look into, essentially doing that. Instead of using the stack. A lot of concepts are simpler for the compiler, but we were just worried essentially about the GC implications of that. How does GC deal with these objects?
Right. So you have to decide. I was doing escape detection, which has the grand benefit of letting you stack allocate things that you know fucking well can escape. They just, statistically speaking, do not. Right. And this is all your error exit paths, all your throw and exception paths, all those kinds of things. So I got a lot of wins, but the side effect is I had to have a read barrier to detect escapes, or write barrier. I guess a write barrier in this case. One of the two is a write barrier to detect escapes, and the write barrier had to be cheap. So I had to have some sort of bit twiddly game that could do the write barrier, and that in turn meant that my heap space, which is well known to the whole JVM and has particular bits for edge cases on purpose for the same reason, I had to fall into that camp and get a similar style pattern to go fail the escape test. Once you failed the escape test, you didn't care how expensive you were, basically. Once you failed the escape, you were going to copy a bunch of objects out to the heap. It was all expensive, so I didn't care what happened. I just had to have the cheap test in the first place. But that changed a lot of other design decisions that are interlocked. That's what I'm saying. I don't know. If you don't do detection, you have a different set of choices.
Yeah, at one point we actually worked with a research group when I was on J9 to actually investigate sort of similar, like doing thread local GCs completely. Once we had a region-based collector, we're like, okay, well, we're just going to give not a whole region, but some portion of a region or a whole region to a thread as a thread local, and like just put every allocation there unless it was known to completely escape all the time, and then use the write barrier to copy out things into the normal heap that actually escaped. Just to kind of give us a ballpark on really how much was escaping. And we saw very similar to what you're talking about. Most workloads we ran, it was like somewhere in the 60–70%, but like it was usually that high for most things that never escaped the thread, that they're like truly never accessed, read or written to by another thread.
Yep.
So you can make some really crazy wins if you could do that. Now our mode of doing it, copying every object that escaped on the write barrier, that was really slow, but it was just to research to get the data on how much was happening.
Right. Oh, yeah. So it's escape detection. You start counting escape events from allocation sites. You put counters there.
Yeah.
And then you start declaring at the JIT time that you're going to only JIT the heap or the stack flavor and that kind of shit going on. Yeah. There's a bunch of games you did to get that right, or you pay the cost. Wow. So it's been an hour and a half. Anyone else have any questions they want to bring up?
I still haven't managed to read everything that Matt posted last week.
I have to pick and choose. Some things I'm going to vote that I know enough. I'm not going to read. Like the cuz random scheduler for concurrency. I know what's going on there. And I've done very similar effects. We talked about that already. Yeah, thank you, Matt. No, absolutely thank you, Matt. Because I can always ignore information, but if I don't have it and I need to get it, like I didn't know this JEP existed, right? That's interesting. I think it's a long time coming. It should have happened a long time ago. Fine, it's happening now. Congratulations or good luck to people doing it.
Well, it's not a JEP yet. We're proposing it to be, but hopefully it becomes.
There you go. There are some big wins to be had, and I have totally done long tail 5.9s lowering, distribution lowering on an x86 based collector by basically doing object pooling, basically removing things from the standard GC cycle and preventing them from being GC'd in the first place. The guy claimed it was a 10-fold reduction in his 5.9s, tail number. I don't know what that exactly meant, but he went from 95 to 99 point something % and was very, very happy. And that was a, you know, don't do GC. Everyone loves GC, and also it sucks so bad. It's fine. All right. So I'll wrap this up. I'll claim next week. I'll do a stack-based allocation as a teaser to open. Expect roughly 30 minutes of slides, and everyone's kind of an expert, so I might burn through them even faster. And then we'll just, you know, we'll have a topic already in Q&A on what you guys are doing and how it's different and what I did and what matters and what doesn't. I think that'd be very fun. And I think with that, it's another fun coffee compiler club. I'm having a good time here.
Thanks.
All right. See folks next week.
Yeah.
See it.
Bye-bye.